Hey there, Mums, Alejandro, and welcome back for day 189 of me doing Daily LeetCode challenge. To reach 1 year's worth of great contributions here on GitHub. So today's problem is for January 21st, 2025. And without further ado, let's get straight into it. Okay, today we get problem 2017, grid game. You're given a zero index 2D array grid of size 2 by n, where a grid of RC represents the number of points at position RC on the matrix. Two robots are playing a game in this matrix. Both robots initially start at 0, 0 and want to reach 1, n minus 1. Each robot may only move to the right RC to RC plus 1 or down, okay? At the start of the game, the first robot moves from 0, 0 to 1, n minus 1, collecting all the points from cells on its path. For all cells RC traversed on its path, grid RC is set to 0. Then the second robot moves from 0, 0 to 1, n minus 1, collecting the points in its path. Note that their paths may intersect one another. The first robot wants to minimize the number of points collected by the second robot. In contrast, the second robot wants to maximize the number of points it collects. So this is basic min-max. If both players play optimally, return the number of points collected by the second robot. Okay, so this is going to be dynamic programming. Okay. Eric Dermain has a really... I remember... I mentioned this in one of my DP videos, usually with min-max, the way that I've been coding it is kind of weird, whereas like what I should do is essentially have a dynamic programming function that in turn as one of its parameter takes a boolean, like is player 1 or is player 2. And if it's player 1, then it wants to maximize. If it's player 2, it wants to minimize, right? And that way you can just keep calling the function as the other player. But yeah. Yeah, we can see if we can try that. This would be a good time to practice essentially doing min-max DP, where I try to pass in the player as a boolean flag into the DP function, right? So here we'll do DP def DP self, comma, robot 1 pause, robot 2 pause is robot 1 turn, right? Something like that. Okay, let's look at an example here. Oh, wait. Oh, wait, no, this is easier than that. Essentially, if you want to minimize the second robot's score, don't you just, like, okay, this is easier than just dynamic programming, right? It's just traverse the graph to find essentially the path with maximal cost, right? So if anything, we can use, like, a max heap and just do reverse UCS until you reach the goal state. Right, mark all those as visited, and then just redo UCS with the second robot, where it's like if something's been visited, then its cost is actually 0. Right, that's essentially how I would do it, right? Here, yeah, this is the most expensive path, right? From here, it's like you chose this option, then this option, then this option, right? And from here, it's like you still try to maximize your path. Yeah, here they took the most possible expensive path. 1, 3, 3. Interesting. Would it not have been 1, 3, 3, 3, 1? Oh, can it only go right or down? To the right or down? Yeah. So the total neighbor. Yeah. So we don't need DP for this. Okay. Idea, as robot 1. Find the path with maximal cost. Can just use UCS/Dijkstra's algorithm with a max heap instead of min heap. Then all the visited cells along the path should be marked as 0. Right? So we should keep track of the path as we do things, right? So here we'll do max heap is equal to this. Here we'll have negative cost, where cost is negative since simulating max heap with min heap. Cost here we'll say negative cost. Here we should have cost ij comma path. There you go. And here what we'll say is and yeah, the path, so that we can essentially mark them as visited or like, you know, as zeros later on, right? So at the very beginning, here we'll do max heap dot append. We'll have a cost of 0 initially. We'll be at cell I equals 0, j equals 0, and the path will be an empty set. Right, and we'll put ij positions in there. Okay, cool. Here we'll say while length of max heap greater than 0, we'll do heap q dot heap pop from the max heap. Say cost ij path equals this. Cost equals negative cost. Negative cost. There you go. Okay. Then we'll say if check if reached goal state. I is equal to m comma n equals the grid, length of grid of 0. Assert m equals 2. I equals m minus 1 and right, yeah. J equals then optimal path equals path and break. Here at the end we'll say assert optimal path is not none. Or if anything, for now we'll make this an array. Right? Okay. What I need is water, not naked. Here, otherwise, visit neighbors. You'll say directions is equal to right comma down. So right will be 0 comma 1, down will be 1 comma 0. For di dj in directions, neighbor I, neighbor j is equal to I plus di, j plus dj. Lambda inbounds. Inbounds equals lambda I comma j, 0 less than or equal to I less than m, and 0 less than or equal to j less than n. Okay. If not inbounds, neighbor I, neighbor j, and continue. We also need a visited set. A equals set. If here we'll do 0, 0. He'll say, yeah, I, comma neighbor j, and visited. Actually, you can't really visit something again, right? Because you're only going down or right. You can't go back. We probably don't need a visit set. Yeah, I'm realizing we probably don't need a visit set. Yeah, because you can only go down or right, so it's like you're never going to come across, right? It's important when you can go down, left, right, or up, right? Because you could go right and then back left, and then it's like, okay, you want to prevent going back in cycles. But here, if you can only go right or down and so on, you'll never go back to a square you were initially. So that's actually kind of good. We don't need a visited set. If not in bounds, then what we will say is otherwise, if it is indeed in bounds, here we'll do max heap. Yeah. Heap q dot heap push into the max heap. We'll do negative cost minus points is equal to grid of neighbor I, neighbor j, wait, how do they grab points? Do they always grab the points of the first cell? Yeah, right? So the initial cost is grid of 0, 0, right? Then negative that. Yeah. So it's at least a 1 by 1 grid. So yeah, it always starts there. Yeah. So it initially starts at this backline. So yeah, and then whenever it visits the neighbor, it grabs those points. So yeah, points is equal to this. We'll do negative cost minus points, so we keep things negative. Right? Otherwise, we can do cost plus points, and then take all of this and make it negative, right? And maybe that's more understandable. Here we'll do here we can do negative cost plus negative points. We'll do negative points is equal to this. And here we'll say we need neighbor I, neighbor j. We'll do path plus, so we concatenate two things. Neighbor I, neighbor j. So here this will initially be 0, 0. Right? Print f string optimal path equals f string for I, j, optimal path equals and then sum of this equals, okay? So is this 2, 7, so this is 10, so that's 13, right? So 2, 5, 5, 1. Great. Okay, so we took 2, 5, 5, 1 there. Here, what do we take? We take 3, 8, 5, 2. Absolutely fantastic. And over here, what did we grab? We grab 1, 3. Okay, here it thinks that you can go 1, 3, 3. Oh no, this is bad. Yeah, because it's gonna prioritize getting to the end goal. Yeah, it's gonna be greedy. Okay. Yeah, but then if we do negative edge weights, then we can't do Dijkstra's, right? So then do we need something like Bum Ford? Here what we can do is instead of breaking, we'll just keep going. Infinity. If cost greater than optimal cost. Optimal cost equals cost. Something like that. This should be the float negative infinity. My bad. Okay, so for this we still have 2, 5, 5, 1, which is great. Here we have 3, 8, 5, 2, which is great. And then here, moment of truth, we've got, yeah, 1, 3, 1, 15, 1. Okay, so we can keep doing it until we've reached everything. Now the only problem is that that might be every single grid in this cell, right? So what's 2 times n? How big is n? N is 5 times 10 to the 4. So if we do 2 times that, it'll be 10 to the 5. We can absolutely afford to do that. Okay, we can absolutely afford to do that. That is not a problem in the world. Okay. Yeah. Anything at that point, we don't even need to use a max heap, right? Yeah, we probably don't even need to use a max heap. We can just do fringe or q equals collections dot. Well, you know what? For now, let's just use the max heap. Let's just make our life easy. But to do can probably use a regular q here instead. Dot. Okay. So we can do that because we're just going to visit everything anyways. We're not going to greedily do things, so we might as well just BFS our way through, right? Instead of doing some fake UCS where we end up searching through everything anyways, right? We could even do DFS, right? The point is if we're going to search everything anyways, then we might as well do everything, right? Right, we might as well even like do DP. Right, where it's like we do DP, it gets us the optimal path, right? The highest cost path. Yeah. Yeah, the DP is good for this, where it's like, you either go up or left and so on from the end all the way up to the start, in which the start, the base case value will be just 0, 0, and having 0, 0 on the path and so on. It's the same thing. Anyways, so now what we want to do is it's essentially the exact same thing. So here what I can do is call this def helper and do all this. And make it return up more cost, more path. And then here be like print f string helper equals. Okay. Underscore comma optimal path equals helper. And here we'll say for I comma j in optimal path, grid of I j equals 0. Optimal cost comma this equals helper, return optimal cost. Okay, that's accepted. Let's submit. Maybe a little bit slow. Wrong answer, interesting. Interessante, eh? Wait, I'm confused. Isn't there... Okay, so is this basically proof that taking the most expensive path is not always the best thing to do as player one? Essentially, you want to make it so that it minimizes player two, right? The thing that comes big time to mind here is dynamic programming. It's just we gotta make sure that we fit this right in terms of the context of the problem. 2551, eh? It's kind of too long an example here. Set out of 109, eh? So what if we did dp of ij is the cost of the longest, is the maximal cost path from an ij, right? And then essentially what you would do is be like, okay, starting from 0, 0, I'm always going to eliminate the one that gives the maximal cost, right? Something like this. J. Idea. Good game. Good game. Old. Or naive. Here we'll say idea. dp of I comma j. Then, first player should always... Oh no, but if he picks one option... No. If he picks... Since it's always like a DAG, right? If it's the same... If it's the same, then the values matter. Yeah, going down is kind of like bad. So it's about when to go down, right? It's about when to go down. Right, because once you choose to go down, it's locked forever. Right, so now this is interesting. Here we'll put a cache decorator. Here we'll say if we'll do the same thing here. Self.m. We'll just do that quickly. So, grid game naive grids. Sorry. Just want to make sure that I write this down. To see if there's a difference later on. Because the question is, when does it make most sense to go down, right? That's the whole problem. You keep going right until you eventually go down and then keep going right, right? Like, yeah. So the question really becomes, when do you go down? And you really have n options, right? Which again feels very DP-like. If you choose to go down at index I don't know. I don't know, right? Because this example kind of proves an annoying case where it's like here they can totally just keep going until here. What? It's like I could do I could solve the problem where it's like I choose to go down for every single index I. And for each of those, it's like, what is the best path, right? The only problem is that there's up to n index i's, and this squared, it's not. Yeah, I can't do this squared. Okay. I need a linear relative solution. Right, but with the DP thing, I can always close off what is the more costly path from where I currently am, right? Which is awesome. But I don't know if it'll make a difference. Self. Okay. What? What? Am I modifying? This is case 1. What is grid equal? the heck? It's just weird. No, not this. There we go. Okay. Okay, so it says here's 13. And it's like 11 from here or 7 from here. 1, tak. Right, so we can assume that player 1 will have made it so that every single cross point, you cannot pick the one that is maximal. So we can do it so that you must always pick the one that is minimal, right? We'll say if I equals m minus 1 can only go right, plus or equal to j plus or equal to 1. So either can only go right, can only go down. If j equals n minus 1, rid of ij, I plus or equal to 1. N minus 1, n minus 1. Here we'll say, yeah. That's fine. Can only go right to either add grid 0, 0 or grid of m minus 1, n minus 1. We'll have to make a decision which one we do later. All right, otherwise we can go either one, right? If self.dp of I plus 1 j less than self.dp of comma j plus 1, then we'll choose to go that way. Plus or equal to grid of ij. Here we'll say this. J plus or equal to 1. Cost plus or equal to grid of ij. Every single time. minus, or over here we can do 0, 0. And no matter what, if elif else, and here return cost. It's wrong in all cases. Interesting. Nine. What the heck? Well, this will be 0 no matter what. And also, yeah, we need to make sure that we know that the maximal path cost. Okay. Let's first paint maximal path cost as all zeros. Grid of ij will become 0. Here we'll do something similar here. If I is equal to minus, can only go right. This is greater than or equal. Well, okay. Let's think about the equal case, right? It's always better to be above. So yeah, if the above is the same price, we should stay above, right? No. Only if it's larger. Let's try to be greedy for now. Yep. F string grid equals, and here we'll do F string grid equals. Yeah. Here we'll say that. We'll say grid of j equals 0. So on. So yeah, so now this is 0, 0, 4, 1, 0, 0. Now we'll try to take the maximal cost path. I will use this helper right now. If anything, we'll have it like this. We'll take in a self. I'll say, and I'll take in a grid. Grid f string path of grid equals. go. Four, 4, 7. Here we still get 96 though. Interesting. So even by clearing, yeah, okay, so even by clearing the maximal cost path, so it's gonna be one of these things where it's like, you can't simulate because you don't have enough time. Yeah, interesting. I mean, this problem really screamed dynamic programming to me from the very, very beginning. Yeah, if I do the UCS kind of thing at the end, that's totally fine. So it can't be based off an initial maximal path. There's something different here. I need to watch those grades before I eat them. Jeez. Okay. Yeah, interesting problem. Okay. Clearly, you want to get to a point where essentially you want to make sure that you decide when to go down. I can't do a max path controversial every single time though. This is like min cut max flow. Right, because there's a reason why it's 2 by n and not like m by n, right? Because otherwise they could make it like m by n and it's like total number of squares is linear. The point is that you go down once. So it's like figure out when to go down as the first player. Right, if I go down here, actually, if I choose to go down here, my robot has 2 options, right? Number of points up to here, number of points, right? Essentially, it has all the points it can get from here, or all the points it can get from here. Ooh, right? Here's like all those or all these. Right here's all the, I think we cracked the code, ladies and gentlemen. Yeah, so, yeah, you want the one that minimizes it, right? Yeah, okay. You know what? We're just gonna restart this problem. Okay, idea. The fact that grid is of size 2 by n is not a coincidence. The point is that player 1 must choose to go down exactly once, and every other action will be to go right. We want to find the best point in time to choose to go down such that it will minimize player 2's score. Since every cell we traverse sets the value of that grid to 0 as player 1, then for every index I, if player 1 chooses to go down at index I, obtain is one of the following. 1, the sum index i.e. grid of 0, I plus 1 onwards. 2, the sum of the elements in the row before index I, i.e. grid of 1 up to I. So we need to suffix sums the top row, well as prefix sums the bottom row. Then we will be able to compute two possible index I two options. So we assume player 2 optimally and minimizing this result. Okay. Top row suffix sums top suffix of index I equals grid of 0. Ideally, we'd like this to be index I plus 1 onwards. Right, we'll say cur sum 0. For num in grid 0, cur sum plus or equal to num, top suffix, top, wait, do we want suffix sums, right? So here, what do we want? We want reversed. We'll make this a collections deck. Append left. Bottom prefix equals this. cur sum equals 0 for num in grid 1. Cur sum plus or equal to num. Bottom prefix append cur sum. Print f string top suffix. Print f string bottom prefix equals. Let's see. So here says, yeah, that's 11. Here you can only do 9. Here you can only do 4. This is up to this index line inclusive. So if we want it to be not inclusive, then we need to put like a dummy node in there, right? But yeah, okay. So what we'll say is layer 2 score infinity min player 2 score we'll say for j here we'll say case 1 equals top suffix. We want from index I plus 1 onwards, right? So here we want I plus 1. It's in length of top suffix else 0. Case 2 equals bottom suffix of I minus 1 if I is 1 greater or equals 0 else 0. 2 score equals max of case 1 case 2 min player 2 score min of itself and player 2 score return itself. Does that work? Bottom prefix, yeah, my bad. Okay, that's accepted. Let's submit. Okay, there we go. Completion streak 189 days. Consistency is key. See ya tomorrow. Okay, that's actually a really clever solution right there. Okay. That's actually kind of nice. I didn't think about that immediately. It took me a little while. It took me an hour to realize that. But yeah, that's actually a nice, neat little trick and so on. This one did indeed take me a while. So now we can just do a few minute optimizations, right? Here we can say like, you know, yeah, if I plus 1, right? So something we, so for sure, is if I do I, and here I give it a value like 0 here, what happens? No. Doesn't like that at all. Oh, top suffix. Actually, we can just do a 0 here, right? And then we can get rid of this guy right here. Yeah. If I put a 0 in this guy, this needs to be an I, right? Yeah, so that's fine. So now we don't need to do those if statement checks in there. So that barely makes things better. What if I, instead of a collections of deck, we have an array of 0. Something like this. -1. And now this guy should become, it stays at I+1. So does this work? Okay, so that's definitely a lot faster. That's good. That's good, that's good, that's good. None in grid 0 backwards. Is that faster? Maybe a little bit. Okay, nice. We will say I+1 is equal to the thing we want, I guess. Yeah, a little bit weird. There we go. Yeah. To score case 1 if case 1 greater than case 2, else case 2. So this should work as well. So this should make things a little bit faster too. Yep, and then here we'll say layer 2 score greater than this guy, else this will become, actually, this will become player 2 score like this. This should be less than. Or actually, here we'll say less than min player 2 score. And then min player 2 score equals player 2 score. And then we can get rid of this guy. Okay, let's run this. Okay, now submit this, and this should be a lot faster. Okay, there we go. 54 ms beats 98.69% of solution. So we went from 5% to 98% just by fixing O1 stuff, which always feels nice and amazing because LeetCode is just random like that and so on. But yeah, sometimes it's just like, okay, when you find an optimal solution like this, then it just comes down to the point of just like, fixing the O1 stuff so you can beat the others. And I kind of enjoy doing that now because it's just a little fun challenge after doing the actual LeetCode challenge every single time. So there we go. And also it's like, it helps you understand of like, what's better. Even just because something is O of 1 doesn't mean that you should always do it, right? Like, it helps me learn like, as an engineer myself, like, always try to do things that are better. And so it's like, oh, I understand, like, array indexing is faster than hash map lookups and so on, even though they're both constant time. It's just, prioritize the faster things whenever you can. Okay, so nevertheless, as always in all my videos, I do a quick recap if I was able to solve the problem. So for this one, essentially, it was kind of a deceiving problem because I was trying to go down routes that didn't work. One of them was essentially like doing some, essentially, my first idea was like, by the way, the point of the problem is essentially you have a grid. Player 1 is able to traverse the grid, and whatever traversal they choose, and it's a 2 by n grid, so 2 rows each with n columns. Essentially, as player 1, you traverse a path from the top left to the bottom right, and once you do so, all the squares that you visited, you make them 0, right? And you want to essentially visit the path such that it will minimize player 2's best score, right? So for example, here, if I choose this path, right, then this becomes a 0, 0, 0, 0, and then player 2's best path is coming down here and getting a full score of 4, right? So it's kind of like a typical minimum minimax type of algorithm. And so my first idea was like, okay, essentially let's find the maximal cost path and then essentially like, make them all zeros, right? Which would be a greedy approach, but turns out that greedy approach didn't work. And then I was like trying dynamic programming where it's like, okay, what if we keep track of like, maximal path at each step, right? So it's like best possible cost path from here, and so on. But and then it's like, always make sure to lock in the decision that is essentially of greater cost to essentially screw player 2 the most. But turns out that's the exact same algorithm at the end of the day, since it's a 2 by n grid, as it would have been to essentially just eliminate the maximal cost path. So then I was starting to run out of ideas, and finally I realized something, which is that the fact that this is of size 2 by n should be suspicious right off the bat, right? This is not completely random. And what I realized is like, okay, essentially both players are going to keep going right, except at one moment they're going to choose to go down, and then for the rest of the problem they'll keep going right, right? For example, here they chose to go right 0 times, immediately down, then right the whole rest of the problem. Here they chose to go fully right and only at the end go down, right? But the point is like, you'll go right a bunch, some point which might be 0 more times, you'll go right 0 or more times, down, then right 0 or more times, right? So the point is you go right about 0 more times, down, then right 0 more times, right? So, and that's going to be for both players. So essentially, I can think of it as like, okay, when does player 1 end up going down, right? Now, I could try every single possible case, right? Where it's like, it tries to go down at every single index I. And it's like, okay, maybe I could do a breadth first search from like, the top left to the bottom right, where it's like, anything that it would have traversed is essentially a 0 and so on, and then try to find the score. But then I realized that like, okay, if I choose to go down at a certain point in time, right, for example here, then essentially I know that everything on the top row up to this index will be zeros, right? Then I choose to go down here, so everything from here and rightwards will also be zeros, right? But from this index where I chose to go down, everything to the right will still not be zeros. And from where I chose to go down here, everything to the left of this square will be all the non-zeros, right? So player 2 can either essentially grab all of the values to the left of the column that I chose to go down on the bottom row here, right? Or on the top row, where and the index I that I chose to go right, grab all the guys on the right, right? So here, for example, we chose to go here. So the only things to the left of this guy is this 1. The only thing to the right of this guy is this 4. 4 is better than 1, so we grab the path that has the 4, right? Over here, for example, it's like we have 0 elements to the left of this 8, right? So there would be a cost of 0 here. But here, after this 3, there are 2 elements, this 3 and then 1. So this is 4, over here 0, so the better path is grabbing those 2, right? Here in this example, it's like, okay, to the right of this guy, there are no elements. But to the left of this guy, there's 3 elements, so 3, 3, and 1 gives us a total score of 7. So let's grab that path as the second player, right? So that is a way to reframe the problem, where it's like, essentially as player 1, at some point you have to make a decision to come down. Whatever column you choose to come down on, right? The only 2 possible scores that player 2 can have is essentially, okay, whatever column you chose to go down on the top row, it can grab all the elements to the right of that index I. For the bottom row, it can grab all the elements to the left of that index I, right? So what's the best data structure to essentially help us out in this case? prefix and suffix sums, right? For the top row, what we're going to keep track of is essentially like, you know, for any index I, be able to quickly look up what is the sum of the numbers from that index I onwards, right? So that way it's like if we choose to do like at this index I, right? For example, we choose to go down as player 1, then we can be like, okay, from this is our index I. We want from index I plus 1 onwards, what is the prefix sums of this row, right? So that way it would be like from this index onwards, what is the sum of the values in this row, right? In this case, there's just one element, so it would be 4. But you can imagine for something like this, right? It would be like the sum from this index forward would be a total of 4, right? So we can keep track of suffix sums, sorry, for the top row, right? Because it'll be from an index I onwards. For the bottom row, we can keep track of a prefix sums, right? From index 0 up to an index I. And that way it's like if we chose to do an index I is where we go down as player 1, we'll say up from 0 up to index I minus 1, right? So if this is index I, this will be index I minus 1. We want all the values from 0 to index I minus 1, right? And so that way, what we can do is, as player 1, we'll consider every single index I that we go down, right? So here it's like, you know, for every single I in range length of greater than 0, we'll do, we'll say, okay, if we go down here, essentially, by the way, you'll see I plus 1 and I and so on here. You'll notice that essentially I kind of did some micro optimizations here. But if I honestly kind of like undo a lot of my code, I'll get it to a spot where it's a bit more readable. Here, I'll get it to, yeah, let's get it to a spot where it's a bit more readable. Yeah, there we go. So, okay. So now, here we have, okay, so here we'll iterate over everything. Here we have a top suffix and bottom prefix arrays, right? Top suffix, essentially collections.deck, current sum is equal to 0, go through the numbers in reverse order, add the current number to the current sum, and append left to the top suffix and so on. So that way it's like top suffix at index I will be the sum of the top row from index I onwards, right? Bottom prefix will be the same thing. Start from an empty array, current sum of 0, loop through all the numbers in the bottom row, every single time adding that number to our current sum and appending that current sum inside of bottom prefix, right? That way bottom prefix at index I will be the sum of the elements in the bottom row from index 0 all the way up to that index I inclusive, right? So that way we can loop over every single index I inside out of n that we have, right, which will be the length of either the top row or bottom row. And then we'll say, okay, if we choose to go down as player 1 in this case, then player 2 has basically 2 possible scores they can grab, right? Essentially the sum of the elements after the index I in the top row, or the sum of the elements before index I in the bottom row, right? So case 1 will be like, you know, it grabs the things in the top row. So it'll be top suffix, remember, top suffix of I is equal to the sum of the elements in the top row from index I onwards, right? If this is our index I, then it can only grab elements from the top row from index I plus 1 and onwards, right? Because again, index I is set to zeros, right? So here will be top suffix from index I plus 1 and onwards. And that's if I plus 1 is less than a length of top, otherwise 0, right? So if we're like, you know, at the very, like for example here, if we're at the very end, like there's no more elements to the right of us, right? So it would be just 0 in that case. So that's kind of the point that I'm trying to make here. But the point is like, you know, we get the suffix sums from index I plus 1 onwards, right? Because index I itself is set to zeros, right? Case 2 would be like, okay, in this index I column here, we'll say of sorry, this should be bottom prefix, yeah. The prefix sums from up to index I minus 1 inclusive, right? Because if this is index I, then we want all the way up to index I minus 1 inclusive, right? So all the elements to the left of index I. So from 0 up to I minus 1 inclusive, right? And if I minus 1 is greater than or equal to 0, otherwise 0, right? So obviously, if we're at the very left, like this case, there's no elements to the left of us, so it's just 0, right? So these are the 2 possible scores that player 2 could get, right? There's no reason why player 2 shouldn't just go horizontal the entire way and then down, or down and then horizontal the entire way, right? Because the point is that like those are the only 2 possible ranges of non-zero values that it can grab from. So either it'll grab all the ones here or all the ones there, right? So between the 2, obviously player 2 is an intelligent agent, so it'll just grab whichever one is larger, right? Between case 1 and case 2, it'll take the max of these 2 things, right? And then obviously as player 1, we want to minimize player 2's score. So for every single index I, we say to ourselves, this is the maximal score that player 2 will be able to get here, right? So every single time for each index I, we'll set min player 2 score to the minimum between its current score and the score that we just found here, right? Because we're going to loop through every single index I, and find the maximal score that player 2's score could get if we chose to go down at this index I. Out of all these possibilities, we want to take the minimal one, right? We want to find which index I to essentially go down on as player 1 to minimize player 2's score. So we'll go through each case where we say, okay, what happens if I go down here? What happens if I go down at index I equals 0? What happens if I go down at index I equals 1, index I equals 2, all the way up to the very end? So for each case, we'll say, what is the maximal score that player 2 can get? Okay, this is the score and so on. I will keep track of whatever was the lowest possible maximum score that player 2 could have gotten out of every single index I, and I'll choose that index I, right? So that's kind of the point. So out of every single index I, we compute the maximum score that player 2 can get, and at the end, we're interested in the minimal one, right? We want to make player 2's get the smallest possible score total, so we'll get the minimum score out of the scores that player 2 would get in every single scenario, right? And so that's why we keep saying min player 2 score is equal to the minimum between the current minimum player 2 score and player 2 score, which I initialized to float of infinity, so that at the very beginning it's like, you know, it's just this player 2 score, right? And then I just return that player 2 score. Now this solution is just a little bit inefficient because the O of 1 stuff here, doing max and min, is a little bit inefficient. So that's why I did a bunch of edits to the code over here that makes it a little bit less readable. In my opinion, just because it's like, you know, this is just a little bit more annoying to read, this is a bit more annoying to read, like, you know, a top suffix of I plus 1 still makes sense, but I doesn't make so much sense, and so on, blah blah blah. But like, you know, I wanted to at least explain it in terms of, like, you know, the code that I thought was readable, but I'm keeping it as this way just because instead of having, like, you know, a 5% solution, we have a nice and crispy 98.69% solution, and I enjoy making things faster whenever I can, right? The things that are faster here is, like, you know, using string slicing instead of reversed, making sure to use, like, you know, a regular array instead of, like, you know, using a collections.dict, so instead of dex, sorry, so instead of using a collection double-ended queue and appending left every single time, we just use a normal array, append to that array, and at the very end we just reverse it and so on. So just like me doing like small O of 1 optimizations was like, okay, doing this instead of using the min function, doing this instead of using the max function, sorry, and doing this instead of using the min function, so just tiny O of 1 little changes just to get me to that, you know, faster runtime algorithm. But at the end of the day, the time complexity is the very same. And speaking of time complexity of this will be O of n, and this will be O of n, each case doing O of 1 work. So it'll be an O of 3n is equal to O of n algorithm, where I'm speaking of this n over here, right? So this is a 2 by n grid, so it'll be O of n based on this value of n. Well, I can even say based on the size of the grid, because 2 times n is O of 2n is already O of n, so it'll be the time complexity will be dependent on the number of elements inside of the entire matrix, and there you go, bada bing, bada boom. That is the time complexity. It is linear in terms of the size of the grid. So very nice and efficient solution, and here I kind of have it a little bit in writing, which feels absolutely nice and amazing. So yeah, kind of a nice and cheeky problem. I didn't realize what to do immediately, but I'm glad that I was able to realize it at the very end. And yeah, just nice and cheeky problem. I actually kind of like this problem a lot. It was definitely very suspicious to give us a 2 by n grid, I will admit, and I should have caught on to that idea a little bit earlier rather than later. But hey, at the end of the day, we still caught it. We still have a good solution. We have a nice and efficient solution, which feels great. So there we go, bada bing, bada boom. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.